Now let's discuss components of a vector in two dimension. We'll consider first a point P. So let's say P is the point with coordinates x, y. Now with respect to the origin of this coordinate system, we're going to join point O and P with a directed line segment going from O to P. OP is going to be, vector OP is going to be the position vector of the point P, because this is the definition of a position vector. It's a vector which joins any point with the origin of a coordinate system. Our goal will be to find out the components of this vector OP along the x-axis and the y-axis. For this, what we'll do, we'll drop a perpendicular from the point P on the x-axis as well as on the y-axis. Let's say the perpendicular meets the x-axis at the point M and meets the y-axis at the point N. Now what we'll do, we'll consider OM to be a vector going from O to M, ON to be a vector going from O to N, as well as MP, a vector going from M to P. Now let's consider the triangle OMP. Now in this triangle, we can apply the triangular law of vector addition to get OM vector added to MP vector. This is going to be equals to OP vector. Now what is OM vector? We can express OM vector as, let's take only the magnitude OM. However, we have a vector here, OM vector, but once we consider its magnitude, we'll also have to take care of its direction. So what we'll do, we'll multiply it with I cap. I cap is the unit vector along x-axis. So that means, in other words, OM vector can be also expressed as the scalar OM times the unit vector I cap. Similarly, MP vector can be expressed as take the magnitude of MP vector and then multiply it with J cap. J cap is going to be the unit vector along y-axis. This is going to be our vector OP, which means we have x times I cap. Now x, because OM is nothing but the x coordinate of point P, and MP, magnitude of MP, is the y coordinate of point P. So we have x I cap plus y j cap. This is going to be OP vector. In other words, we have expressed the vector OP, or we can say position vector of point P, in terms of its coordinates as x times I cap plus y times j cap. Fine. So this is how we can represent the position vector of point P. Next, we will define the magnitude. To find out the magnitude of OP vector, what we'll do, again in the same triangle OMP, we have OP squared. We're only considering the magnitude. So OP squared will be equals to OM squared plus MP squared. This is the Pythagoras theorem that we have applied. And we need OP. So that means OP, or simply the magnitude of OP, this is going to be equals to the square root of x squared plus y squared. So we have also defined the magnitude of the position vector OP. Okay, now let's go to the next part. Now here we have considered only a single point P, and this is the position vector. Now what if we have two different points on the same two-dimensional plane? Now before moving on to the next topic, let's add a few notes here. Now, here I cap and j cap talks about the direction. I cap is the direction along x-axis, j cap is the direction along y-axis. Now, what if I cap and j cap are negative? If we have negative I cap, that means this is along the negative x-axis. The direction is along negative x-axis, and if we have negative j cap, then the direction is going to be along negative y-axis. Which means that, for instance, if we say that OP vector is given by negative x I cap plus y j cap, then in that case, the x component, which is x here, is going to be along the negative x-axis, but the y component is going to be along the positive y-axis. Okay, now let's move on to the next case. Now let's consider 2 points, point A and point B. Now, point A, let's say it has the coordinates x1, y1, and point B has the coordinates x2, y2. Now, we'll be joining point A and B with the help of a directed line segment going from A to B. Our goal will be to define the vector AB. For this, let's do some construction. We're going to drop a perpendicular from point A on the x-axis and also another perpendicular from point B on the x-axis. Let us suppose that the perpendicular from point A meets the x-axis at the point M, and the perpendicular from the point B meets the x-axis at the point N. We're also going to drop a perpendicular from the point A on BN. So we'll suppose that the perpendicular drawn from A on BN meets at a point F. Fine. Now what we have here is we can define the length AF. Now the length AF is going to be equals to the length ON minus the length OM. Now what is ON here? ON is going to be the x coordinate of point B. So that's x2. And from here we're going to subtract OM, and OM is going to be the x coordinate of point A. So that's x1. Similarly, we can find out BF as well. So BF is going to be BN minus FN. BN is going to be the y coordinate of point B. So that's going to be y2, and from here we're going to subtract Fn. So Fn is going to be the y coordinate of point A. So that's y1. So here we have obtained AF and BF. Now what we'll do, we'll suppose that AF is a vector going from A to F, and FB is a vector going from F to B. So we will consider the triangle AFB and apply the triangle law of vector addition to define AB vector as AF vector added to FB vector. So AF vector is going to be represented as, take the magnitude of AF and multiply it with the unit vector going along x direction. So that's I cap in our case. And we have FB vector, we can represent it as, take its magnitude and multiply with the unit vector along y direction, which is j cap. So AF vector, we have already defined it as x2 minus x1. So we have x2 minus x1 times I cap added to y2 minus y1 times j cap. So this is going to be our vector AB. So here we have successfully defined the vector AB in terms of in terms of the coordinates of the n points. Now that we have AB vector, we can also find out its magnitude. So magnitude of AB is simply going to be equals to the square root of AF squared plus FB squared using the Pythagoras theorem, and this is going to be equals to the square root of x2 minus x1 squared plus y2 minus y1 squared.